Well, good morning. Can you hear me?
We can.
Yeah.
Yep.
Can you see me?
Yes.
Right.
Yeah.
So I am thankful to the organizers for this meeting and for the invitation. Besides, I am admiring Frau and Herr Herius for their wonderful deed. I got the fortune a few years ago to attend another workshop at the site, at the spot, and it was lovely, close to the riverbank of the Rhine. And I hope next time we will see the site itself together. Now, coming to my topics, it's partly technical with some physics, some motivations. For some, it may look a bit formal, but I want to clear up the philosophy and structure of hybrid quantum classical dynamics, at least a way which is my approach to the issue. So I try to page now. It's not. Right. Okay. Otherwise, I'm grateful to the organizers that they gathered some colleagues here at the workshop whom I met before and with whom I have some correspondence on the very topics of my talk, hybrid dynamics. Among them, Hans Thomas Elze, Jonathan Oppenheim, Daniel Terno, and also some others whom I never met, but they are also interested and active in investigating classical and quantum systems coupled together that we call hybrid systems. So I have a deliberate list of motivations why people desire hybrid dynamics. In quantum chemistry, the lazy motion of the nuclei compared to that of electrons tells us that we may consider the nuclei as a classical subsystem while the electrons remain quantized. In cosmology, it is a great issue whether gravity itself is foundationally classical, while we know for sure that the matter must be quantized. In foundations, there is a concept that measuring devices be described by classical dynamical tools, whereas the measured system is always a genuine quantum system. And also in open systems theory, the reservoir may somehow be described in classical terms, maybe in dynamical terms, while the system of interest is, of course, a quantum system. And also there is a specific situation in quantum control where the measured signal is classical. It may or may not be a dynamical object, but for sure the control system is quantum mechanical. So these are a deliberate selection of motivations, of possible motivations, why people, including me, are interested in a good and consistent hybrid dynamics capturing a classical subsystem and a quantum system coupled together. Now, let me classify that in my opinion, in my approach, there are three main options to get a hybrid dynamics. So remember, I have a classical subsystem and a quantum subsystem, and I want to create a model, a mathematical model, to couple both of them together. Now, of course, usual quantum systems are described by quantum mechanical formalism. But now I have to do something different. Classical systems are usually, or as a matter of fact, described by classical formalism, say the classical canonical formalism. Now, due to Koopman is a famous formalism, which is a quantum-like formalism, still applicable to classical systems. So we do the following in order to get a hybrid dynamics. We take Koopman's formalism, which is quantum-like formalism, and apply it to our classical subsystem. And now we try to extend, to apply this formalism to the quantum subsystem as well. So there is a way to arrive at classic quantum-like formalism a la Koopman, which extends for both subsystems, for the classical subsystem, which was Koopman's original purpose to describe, also to our quantum subsystem. So at the end of the day, we get consistent hybrid dynamics for both subsystems. There is another option, the other way around, where instead of having a standard quantum formalism for our quantum subsystem, we apply some classical-like formalism. The first example historically was the Wigner function. Here, a remark is in order that because of the possible negativities of the Wigner function, similar phase space quasi-distribution discovered a bit later than Wigner's, which is the Husserl function, seems more suitable to start with. So now, what we do, we have a classical-like formalism for our quantum subsystem, and we extend it for our genuine classical subsystem in a hope that at the end we get a consistent formalism, a hybrid one, to describe and to couple both of them. Now, my way is a third option, which is in the middle. We keep our classical formalism, the canonical one in this case. For the classical subsystem, we keep the quantum formalism, the operator formalism for our quantum subsystem, and we try to unify them, to couple them. And that was done in an elegant way by Aleksandrov, and in an equivalent way by Gerasimenko, who is with us, I think. I'm pleased to have him here. So the resulting formalism is a combined classical quantum formalism, keeping a classical structure for the classical subsystem and the quantum structure, an operator formalism for the quantum subsystem. So let us see the details, how this Aleksandrov Gerasimenko structure hybrid structure looks like. we have the classical subsystem, we have the quantum subsystem, and now let me summarize their own dynamics, their conservative dynamics. The state of a classical subsystem is described by the Liouville density over the phase space. That's the non-negative normalized probability distribution. Here's the Hamilton function, which governs the dynamics of motion. And here you see the equation of motion, which is the Liouville equation. And this bracket is the Poisson bracket in terms of canonical derivatives. On the other side, the textbook knowledge now, and since almost ever, since a century, almost a century, we have the state of the quantum system in terms of the density matrix, rho with the hat, don't forget the hat, to make a difference from the classical density. Here we have the Hamilton operator or matrix with the hat. And here we have the von Neumann equation of motion, where this whole stuff with the prefactor minus I over h bar is also called the Dirac bracket, to have a good comparison with the Poisson bracket on the classical side. Now let's unify those two formalisms to have a hybrid dynamics. The hybrid state is a hybrid density, which is a density matrix and at the same time a phase space density. Observe my tricky way to get a shorthand notation. If I want to spare spelling out the phase space coordinates, phase space arguments, I put a wide hat, a wider hat over the row to have a compact notation for the hybrid state. So do I for the hybrid Hamiltonian, which is a function of the phase space coordinates and the Hermitian matrix. But my shorthand notation is H, uppercase H with a wide hat. And in the wide hat compact formalism, here we have the Aleksandrov Gerasimenko hybrid equation of motion in that compact form. Look here, that's the trivial part, the unitary quantum mechanical evolution in terms of the Dirac bracket. It looks like the von Neumann structure of a quantum equation of motion. Here you have the non-trivial part. This is again the Poisson bracket, but we need to hermitize this structure because H and rho are not commuting operators. So the Poisson bracket of them is a non-Hermitian operator. So we need to take, according to Aleksandrov and Gerasimenko, you need to take a Hermitian part. Okay, that looks a wonderful unification of classical and quantum formalism. For more readability, I display the detailed form of this wonderful equation. So here is the compact formalism with the white hat object. And here you are, the detailed form of the equation, where I retain the phase space dependencies. So that's the time derivative of the hybrid density, which is density matrix and the phase space distribution. That's the trivial part, resembling standard equation. And that's the non-trivial part with the Poisson bracket, now developed in details. And you see that it is indeed non-Hermitian in itself. Now that's a useful effective dynamics, but it is inconsistent mathematically for a very simple reason. We got a very simple example to show the defect, the mathematical defect of this AG hybrid dynamics. We considered in 2000 a 1D classical motion of a classical particle that is coupled to a Pauli spin, which is the simplest quantum system. So here we have the hybrid Hamilton, which is a function and a Hermitian operator at the same time. This is the Hamiltonian of the particle, and this is the Hamiltonian of the spin, and that's the couple. That's the coupling. P is the momentum of the particle, and here we have the third Pauli matrix. Kappa is the coupling strength. And it is very easy, as we showed in 2000, to construct an initial state which is under the evolution prescribed by this HE hybrid equation, acquires a negative eigenvalue. So this HE hybrid equation can distract the positivity, the due positivity of the hybrid density, which is too bad. However, as I said, this equation is quite useful and effective dynamics in some situations. So what shall we do against this mathematical inconsistency? In 95, I got an e-print which remained unpublished, where I solved the issue and I improved on the HE hybrid dynamics. The method is the following. Let's quantize the classical subsystem temporarily, but use a different H bar from the standard one. And now, in the second step, let's couple it to the quantum subsystem of interest, to the other one. Here we need an ansatz, an educated generalization of the Dirac bracket, the standard Dirac bracket, for the case where one subsystem has a different H bar from the other standard subsystem, which is the quantized one, the genuine quantized one, which holds the standard H bar. So here we have some ansatz, but this ansatz is a very natural one. And then we have the coupled big quantum system. The 2B classical subsystem is also quantized in this approach. And the resulting dynamics is a non-unitary irreversible dynamics. It looks like a quantum master equation, a quantum kinetic equation for the joint system. But if you look at it and you are educated in the theory and analysis got by Lindblad and Gorini and Kosakovsky and Sladershyn long time ago, about how a legitimate mathematically correct master equation, quantum master equation should look like, then you see that your equation with the two Planck constants is an incomplete Lindblad equation. So what to do? It is very easy to complete it, because if you look at it, it's very transparent what and which terms are missing. And you can easily add those necessary terms. And you don't add too many terms, you only add that are necessary to make your master equation a legitimate Lindblad, Gorini-Kosakovsky Sladershyn master equation. And then you take h prime, to 0 to turn your first subsystem back to be classical. That's the way you derive some dynamics. What is the result? The result is a positivity preserving hybrid dynamics, which resembles the Aleksandrov Gerasimenko structure. Okay, let me introduce you into that structure. Here you have the hybrid Hamiltonian. That's the Hamilton of the quantum subsystem. That's the Hamilton function of the classical subsystem. And that's the cup where Q with the hat is some operator, some Hermitian operator of the quantum subsystem, and C is some function over the phase space of the classical subsystem. And that's the compact notation with the white hat. And that's the result of my derivation from 1996. The first two terms are identical to the AG dynamics, which was defectus mathematically because it could violate the positivity of the state. And what I got to cure this defect are two new terms. One new term, which is a decoherence term. For some people, this is well known that such a double commutator structure corresponds to decoherence between dynamical decoherence between the eigenstates of the observable, which forms the double commutator, Q with the hat in our case. And this other term is a diffusion term. Of course, this is which concerns the classical subsystem. This term concerns the quantum subsystem. That one concerns the classical subsystem. We will see at the bottom of the very same slide why this structure corresponds to diffusion. We added the least possible noise to cure the mathematical defect of the first two terms. And as you see, the two terms are governed by a single parameter lambda, which appears here up of the fraction and here below the fraction line. So the bigger the occurrence, the smaller the diffusion can be, and vice versa. This minimum added noise has the feature that the strength of the occurrence times the strength of the diffusion here can be a constant, can be fixed. Let me see an example. It is again our one-dimensional classical motion of a classical particle coupled to the Pauli spin. Here is whatever Hamiltonian for the spin. The free motion Hamiltonian of our particle, and the coupling, the same as before. And now, according to my derivation, the modified AG hybrid dynamics is the following. Here you see the first three terms come from the standard AG unification of classical and quantum dynamics. And as I said, those three terms would not preserve the positivity of the state. These two terms are innocent in that mistake or crime. This hybrid coupling term is responsible for the violation of the positivity of the state. And those two new terms restore the positivity preserving feature of the equation. This is the occurrence term acting on the quantum subsystem. And as you see, if you evaluate this diffusion term, observing that C is just kappa times P, the canonical momentum, then you get a diffusion term in canonical coordinate. And now the positivity of the hybrid state is guaranteed. And what is it good for, and when it is useless? Again, this is nothing new. For the convenience of you, I repeat the new modified AG equation here. That is the same as on the previous slide. And now, what is that? It turns out that this is just a special case of the generic hybrid master equations, which are generic unification of the Pauli classical kinetic equations and the Gorini-Kosakowski-Lindblad-Saderson quantum kinetic or master equations. So this animal is in the zoo of a big collection of all generic hybrid master equations valid for any classical systems coupled to quantum systems. Of course, the formalism and the theory of hybrid master equations is largely phenomenological. They are not really derivable from first principles of classical and quantum dynamics. Now, this equation is very good if the interaction is written in the form of a single product of a classical phase space function times some Hermitian variable of the quantum system. And it is also very useful if the coupling is expanded in this form, which is always possible, but it is not always general and useful. It is useful in electrodynamics, where the coupling is of this form, and it is very useful in gravity, in linear gravity, where the gravity is represented in classical terms and the matter is quantized. And it may be useful in many linearized couplings, wherever you are, maybe in quantum chemistry or elsewhere.
So 10 minutes to the end, including questions.
Pardon? 10 minutes?
10 minutes to the end.
10 minutes. Thanks. I'm about to finish. And this quite elegant hybrid equation is not really good if there is no distinguished preferred unique expansion of the interaction in terms of products, of hybrid products. I come to the first slides, one of my first slides. This is my summary as well. You remember that I showed you three philosophies, basic philosophies of how to get hybrid dynamics in some systematic way. There are many, many other ways which are also systematic or not so systematic, more phenomenological, but I prefer to show up with these three philosophies. This one, where you extend Koopman formalism for a quantum system, where you start from some phase space formalism of quantum mechanics and extend it on the classical system. And when you keep classical formalism and quantum formalism and unify them as I proposed you, there is a modified and improved unification which contains some decoherence and diffusion to achieve the mathematical consistency of this elegant coupling between the classical and the quantum formalism. And I'm sorry, I never compared those three results, but I may suggest as a next research topics to compare these three approaches, just to take the simple example and look at how different or how similar the three hybrid equations proposed in this way, or in that way, which I showed you. Okay, now I talked very little about, or almost nothing about the physics. Why? How shall we interpret the result that we arrive at an irreversible master equation, non-unitary and irreversible, noisy, decohering and diffusive equation? Why is that? Why we cannot have a deterministic dynamics that unifies the hybrid of a classical and quantum system? There is a lot to talk about this. It is now, at least in the community I'm in contact with, it is now folklore or a general, common knowledge that the price you pay for a hybrid dynamics is that you lose reversibility of classical and quantum dynamics when they are alone and uncoupled. And also there is another huge issue. If there are genuine foundational hybrid systems, and as far as we know, the only candidate, still possible candidate, is gravity and quantized matter, because the rest of the world, the rest of the phenomena are quantized. So thank you. I may stop here, and I'm open to remarks or criticisms or support.
Okay, thank you. Thanks a lot. Thank you very much for this interesting and inspiring talk about quantum classical hybrids, the first talk on hybrids of the day. We have questions. First question is from Robert Mackay.
Hi, yeah, thanks for your talk. Why don't you consider Meyer Miller's 1979 classical quantum hybrid, or an equivalent one in terms of Lee Poisson dynamics on density matrices?
What result are you mentioning?
The first one is Meyer and Miller in the context of chemistry. So your very first example, nuclei and electrons. They formulated a classical quantum hybrid in 1979, which you can mathematize more. I've done that, but it's a very natural approach. I don't see what's missing in it.
Is that using a Poissonian structure, Poisson bracket structure, or something else? Where you would,
so the way I formulate is I formulate a symplectic form on a on a vector bundle over the classical state space.
Yeah,
but you can equivalently do as a Lee Poisson.
Yeah, look, I have to seriously apologize towards you, and I guess towards quite many of colleagues, even in the audience, because I have not included their results, even at just mentioning them. My first reason is that I am not really active, or not constantly active in the field. So I may have ignored even the most relevant contributions. And but let me ask you, I'm really interested. Can you tell me if your result fits to any of the three boxes I mentioned?
The three boxes being
the
in this slide. Yeah, so it's the two approaches I'm mentioning are classical formalisms of hybrid dynamics.
Yes, and is it based on the Wigner function?
No.
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 Is that related to any of the well-known phase space quasi distributions, like the Houtsimi function?
No.
Or...
No. No, it doesn't use that at all.
Okay. So I'm sorry.
It's okay. I'm just curious to ask why what your opinion is about those approaches, because for me they're good approaches, but maybe I'm missing some feature that yours is better for.
Yeah,
okay.
I sure it concerns the positivity of the state, if there is any such notion in your formalisms.
For the Meyer Miller, there's no such notion. For the Lee Poisson, it's formulated. It gives the von Neumann evolution of density matrices. So I should check on that. But for the Meyer Miller, then it's in terms of projectivized wave functions.
Yeah, of course, during the workshop, I must have some spare time to look into it. So thank you.
Okay, thanks.
Okay, so next question may be a quick one from Jonathan Oppenheim.
Yeah, thanks, Lajos, for a great talk. So I wanted to just speak in enthusiastic support. You mentioned that there's that your equation only works if you can write the interaction Hamiltonian as in terms of like a C times a Q. And I just want to say at the risk of spoiling what I'll say in my talk, that you can actually generalize it to any interaction Hamiltonian. And maybe the second thing to say is in relation to these other approaches, we've been able to show that if you want continuous hybrid dynamics, that an equation like a modest generalization of your equation is the unique master equation that you can have. So I feel like with these other approaches, there's a bit of a challenge to show, they must in some way reduce to your approach if they're continuous. There's no other option. So I feel like that's in some sense a challenge to these other approaches, which can they show that they're, if they're able to show that they are completely positive trace preserving and preserve the split into quantum classical degrees of freedom, then they must, if continuous, they must reduce to something that looks like your equation.
Yep.
Okay, next question, Daniel Terno.
Lajos, again, thanks for the talk. Nice to see you again. And the question is just so I understand correctly, your take from the talk, from your work is that if you want consistent mixed formalism, it should be stochastic and essentially it's master equation. So forget reversibility.
Yes. Yes, I do.
Okay, no, thanks. That's, well, that's like almost like no free lunch theorems, that there is no free lunch, you have to pay something.
Yeah.
So, okay, thank you.
Yeah, exactly.
Okay, maybe if I have a little time, just one quick question. I am aware that the Lindblad equation does have a H theorem. Your equation, the ideal limit of your equation does not return a Hamiltonian system. So that prompts the question from me: does your model have a H theorem?
You mean something on the entropy, or what?
Well, it's something. It's Boltzmann's H theorem. Yes.
I see. I'm sure since this is a master equation, an irreversible master equation, a hybrid one, but it doesn't really matter. The increase of the entropy or the behavior of the entropy must be the same as in case of a genuine quantized system. I don't think that there could be any problem to derive a similar theorem for the hybrid master equations.
Okay. Well, the only reason why I ask is that I noticed that your equation does not reduce to an ideal Hamiltonian system when you take the irreversibility off. And so that would be the main difference from Lindblad, and this is why I asked. Just wanted to motivate my question more.